Hello. Today we're going to be talking about geometric sequences and series. Now, see, a sequence is geometric if you are multiplying from one term to the next a common ratio. So, for instance, we did one the other day where it was 5 and then 5 halves and then 5 fourths. We were, in essence, dividing by 2, but what that means is we were actually multiplying by a common ratio of 1 half. If you multiply by the exact same number to get from one number to the next, that makes it geometric. Whatever that number you're multiplying by is your common ratio. So if your numbers are increasing, your common ratio will be larger than 1. If your numbers are decreasing, then your common ratio will be between 0 and 1. So take a look at these 4 examples, and what I'd like you to do is identify each as a sequence or series. Say if it's geometric or arithmetic or none of those. And then finally, finite or infinite. So take a look at all 4 of those, pause the video, and try them all first, and then come back here for the answers. So our first one is a sequence. It is geometric with a common ratio of 4, and it is finite. The next one is a series, and while it does follow patterns, it is neither arithmetic nor geometric, and it is infinite in nature. The third one is a series. It is arithmetic because your common difference here is 13, and it is finite. And lastly, you have a sequence that is geometric with an R value of 3, and it is infinite. So we're going to take things that are geometric, and we are now going to write the equation for those. So we used to say geometric is modeled after an exponential function. And exponential functions look like a times b to the x. So when we get to this rule here, it's going to be modeled after that. It's just going to be in your sequence notation. So a sub n is like saying y. A sub 1 is your value of your first term. R is your common ratio. And then to the n minus 1 is going to stay the same. It's like when we did our arithmetic formula and we did n minus 1 to go back a term. This is very similar here. You want to go back a term to find your y-intercept. So looking at this one, honestly, it's much nicer than the arithmetic because once we plug in a sub 1 and once we plug in r, we're done. So looking at this one, we have a sub n equals 5. That's our first term. And then our common ratio, what we would need to do is we need to figure out how do we go from 5 to 2 and 2 to 0.8. You can always take a term and divide by the previous term in order to find that common ratio. So for this one, it is 2/5, and we just leave it as a sub n equals 5 times 2/5 to the n minus 1. So we're going to do the same idea with this next one, except we're given the 4th term. So there's many different ways to do this. Our 4th term here is 3. Our common ratio to get to one to the next is to multiply by 3. So option number 1 is to just divide by 3 until you get to your first term. Once you know your first term, you can go ahead and write 1/9, and then your common ratio is 3 to the n minus 1. And you can always check your answer by plugging in 4 for your n and seeing if that works. If you don't like that, you can use your equation and you can plug in, okay, I know I'm ending at 3. I don't know what my first term is, but they told me my common ratio was 3. And my n for this one was 4. So you can figure out 3 to the 3rd power and divide both sides by 27 to get a sub 1 by itself, and you would end up with this equation anyway. So there's many different ways you can solve for your first term in order to write your equation. So we're now going to be using geometric sequences to find the geometric means, and it's going to be somewhat similar to the arithmetic means, except it's just multiplication. So if you have the numbers 2 and 1,250, the first thing we did with arithmetic, we said, was how far apart are these? But with geometric, it's not something that we're adding. It's what do we need to multiply by to get from 2 to 1,250. So overall, what's happening here is you are multiplying by 625. Again, geometric means you're looking for multiplication. And then you're looking at your common ratio. You have 1, 2, 3, 4 times that you are multiplying that common ratio by itself, which means 625 is going to be r to the 4th power. So in order to solve this, what we're going to do is we're going to take the 4th root here. So r is going to equal 5, but because it's an even index, it could have either been a positive 5 or a negative 5, because we would technically have had the absolute value of r. What that means is I can multiply by 5 each time to get to the next number. So my numbers could be 10, 50, 2,000, or 250. Or I could have multiplied by a negative 5, negative 5. To get negative 10 times negative 5 would be positive 50, and then negative 250, and then positive 1250. So you do have two different sets of answers for this. Both 10, 50, and negative 10, 50, and negative 250 work, but so does 10, 50, and 250. So now we can manipulate geometric sequences, but we're now going to take a look at geometric series. So a series, again, is found by adding terms together. So your formula for this one, it looks very different than the arithmetic one, and that's because geometric sequences and series are very different in their nature. So we're going to use a sub 1, that is the value of the first term. You have r, and then you have n. N stands for your number of terms, and R stands for your common ratio. So sometimes we might have to go hunting for some of these. So let's take a look at example 3. Okay, so we can identify, hey, this sigma here means we are adding together the 4th through the 12th term. I can see that my equation here, this is a geometric equation. Because I have my a sub 1 given to me, a sub 1 in this case is 1/4. My common ratio here is 3, and it's to the n minus 1 power. Now for this sigma, I know it says a sub 1 in my formula, but in this sigma notation, I really don't want to start at the first term. I need to find the 4th term, because that's the starting term for my sum. So I'm going to go ahead and I'm going to take my equation, and I'm going to plug in 4 for n, and I'm going to figure out what that equals. So that's going to be 27 over 4. So to find my sum, what I'm going to do is I'm going to take that term, 27 over 4, because that's the initial term in this specific sigma, and I'm going to do 1 minus my common ratio. Now I already identified it based off of the equation to the n. I'm going to put a pause on that n, over 1 minus r. Now this n here, when we are in sigma notation, you might be thinking, okay, 4th through the 12th term, well, that's 8 different terms, but it's not. When we're in sigma notation, to find our n, we're going to do the top number minus the bottom number, but plus 1, because we want to include our starting amount and our ending amount. So our n value is 9 in this case. At which point we would take out our calculator and we would type this in with parentheses around the numerator and the denominator. And so do 27 over 4 and then type all that in. We should get 66,426.75. So now we can use this backwards. So S sub n equals a sub 1 times 1 minus r to the n over 1 minus r. Here we are told the sum is negative 26,240. We don't know our first term, but we are told that our common ratio is negative 3, and our n value is 8. So at this point, we can kind of simplify some things in order to solve for a sub 1. Our denominator would simplify nicely. 1 minus negative 3 would become 1 plus 3. So we get negative 26,240 equals a sub 1 times something over 4. But in the numerator, you have to be a little bit more careful because you have negative 3 being raised to the 8th power. And you have to do that first. So you'd have to do -3 to the 8th power and then do 1 minus that answer. So you're going to get some number up there, and then in order to get a sub 1 by itself, you're just going to divide this to the other side. So when you do that, you should get a sub 1 to be 16. For the next one, we have given the series, we are told our sum is 820, so we can plug in 820. We can see that a sub 1 is 1, and we can figure out that our common ratio here is 9. Our issue with this one is that we don't know n. So we are going to have to solve for that. It's an exponential function, so we're going to have to solve for it with logarithms. So we're going to first take and divide a sub 1 to the other side, which in this case changes absolutely nothing. And in our denominator, I can also simplify that to be -8. So I'm going to multiply the -8 to the other side and get -6,560 equals 1 minus 9 to the n. I want to get 9 to the n by itself, so I'm going to subtract 1. And this negative is out in front, so I'm going to go ahead and divide by -1 and get 6,561 equals n, or 9 to the n. So I am right now stuck in an exponential form. We're going to have a throwback question to chapter 8. Our base is 9, so we're going to take the log base 9 of both sides. So we're going to do log base 9 of 6,561 equals n. So you can type that in on your calculator to figure out that there are 4 different terms that we had added together with this geometric sequence, or series rather. So thank you very much for listening. I hope this helped. Let me know if you have any questions.